Welcome to our talk on fluidic topology optimization with an anisotropic mixture model. I'm Yifei Li. This is a joint work between MIT, University of Wisconsin-Madison, Tencent Lightspeed Studios, and Dartmouth College. Fluidic devices are everywhere in our lives and are key components in industrial and engineering applications. In engineering, combustion engines compress and combust air to generate power. In bioengineering, microfluidic devices are used to transport and separate particles for downstream tasks. In medicine, research in artificial hearts aim at improving our life, and it's everywhere in our daily life, from water pumps, GPU heat sinks, to propellers, and many more. Currently, the design of these devices still rely on extensive domain knowledge. For example, to optimize the design of a propeller for different flow environments, an engineer needs to modify the design in CAD software, then test it in fluid simulation software such as ANSYS, then analyze the simulation and modify the design, and repeat this whole process many times. Because of this manual design cycle, the design space that has been explored is still minimal, while improving the performance can have large environmental and economic impact. On the other hand, we can adopt an end-to-end computational pipeline that automatically explores a rich design space. Using differentiable simulation, we can start with an initial parameter, simulate the design, then evaluate design defined by a loss function, followed by sensitivity analysis to compute the gradient of the objective with respect to the parameter, then use gradient-based optimizers to find the best design. While the overall pipeline seems rather simple, there are many challenges in coming up with the right geometry representation and accurately simulate the design in a differentiable way. We want the geometry representation to be able to capture a large design space that explores freely for both shapes and topologies, in addition to representing a sharp boundary that enables fabrication later down the pipeline. One representation common in fluidic device design is field-based method, which splits the domain into voxel grids and mark each voxel as either fluid or solid to represent the geometry. This representation can capture arbitrary topology, but cannot express the boundary in subcell resolution. On the other hand, shape-based method represents shapes using parametric shapes such as NURB surfaces. The representation describes the shape boundary exactly, but since it requires a shape prior, topology cannot freely evolve during optimization. For simulation, we need to be careful with simulating the flow at the solid-fluid interface and need to choose the right boundary condition at the interface. Specifically, the no-slip and slip boundary conditions are very important for fluidic device simulation. No-slip specifies that the flow velocity at the interface should be 0 and is used to model the friction between the boundary and fluid in real world. The slip boundary condition requires flow velocity at the interface be perpendicular to the boundary normal, so we need to know the local boundary normal to use slip condition. Slip is needed when the simulation resolution is limited. In this case, if we model the flow going through a narrow pipe using no slip boundary, we'll see the flow having a quadratic profile, essentially being choked by the pipe. To summarize, we need both no slip and slip condition for an accurate simulation. Prior works can be categorized based on their geometry representation. The first class is field-based method, and representative work is from Borrow and colleagues from 2003. As mentioned earlier, this representation is limited by its inexact boundary representation. This poses problem downstream for simulation, where it is impossible to model slip condition, which requires us to know the local normal of the boundary. The second class is shape-based method, and representative work is from Du and colleagues from 2020. Because the method represents geometry exactly, the solver can handle slip boundary condition, but the method disallows topology to freely evolve during optimization. In this work, we propose to use a unified representation of solid phase, fluid phase, and both slip and no-slip conditions through a continuous mixture material model. This means our framework does not assume any shape prior and allows topology to evolve during optimization. Our material model is capable of representing sharp interface with local surface direction, which allows us to model both slip and no-slip condition. I'll introduce our method with the following outline. First, I'll introduce our anisotropic mixture material model and parameterization. Then, I'll talk about the discretization of the continuous problem. Finally, I'll introduce our optimization pipeline and show the designs obtained from our method. I'll start with introducing a material model that can jointly and continuously model both slip and solid phase and different boundary conditions. To start, I'll review Stokes flow in the energy minimization form, since our framework models Stokes flow for the fluid phase. Given a domain omega in either 2D or 3D, we can obtain the governing equation for Stokes flow by assuming the Navier-Stokes equations modeling steady-state, low Reynolds numbers, and laminar flow. We can write down the governing equations of Stokes flow as an energy minimization problem. Here, the notation mu denotes the dynamic viscosity of the flow, lambda denotes the incompressibility, v is the velocity field, omega is the domain we're considering with a dimension d, which is either 2 or 3 in our examples. The two energy terms have physical interpretations that allows us to understand how it models the behavior of Stokes flow. The first term is an incompressibility energy. The second term models the viscous shear stress that exists between layers of laminar flow, which introduces velocity gradients into the flow velocity field. If we take lambda towards limit, the energy models a perfectly incompressible Stokes flow. Now, to jointly model both Stokes flow and solid in the domain, we can add a frictional energy term that penalizes the norm of the flow velocity, along with a weighting term kf. If we take kf to be 0, this term has no effect, and we can retain the original Stokes flow model. If we take kf to limit, this energy term will outweigh the other two energy terms, and the velocity that minimizes the energy will be 0. This allows us to model the solid phase, where we essentially perceive solid as an impermeable medium that blocks the passage of the fluid. We can augment the previous energy terms to rewrite the weighting scalar of each energy in a matrix form. Now, the Km matrix parameterizes the weighting of the stress energy, and the Kf matrix parameterizes the weighting of the frictional energy term. Both matrices are symmetric positive definite with dimension d by d. We can still obtain the previous materials by representing the previous scalar weight as a constant scalar times an identity matrix. To reconstruct Stokes flow, we specify Km as identity matrix and Kf as zero matrix. To reconstruct the impermeable solid phase, we set Kf as a large constant multiplied by the identity matrix. To model no-slip boundary condition, we note that the no-slip requires the local flow velocity to be 0. This is exactly how we model the solid phase, so we can trivially represent the no-slip boundary condition using the same parameters as the solid phase. Now, we showed that our model is capable of modeling Stokes flow, solid, and no-slip boundary. It remains to show how we can model free slip boundary conditions. To do this, we can look at the behavior we want to model for slip condition. Slip conditions specify the velocity should be perpendicular to the local surface normal. This is essentially specifying an anisotropic response of the material in two directions. In the tangential direction of the surface, we want the material to model Stokes flow, while in the normal direction, we want the flow to be impeded. We can achieve this behavior by using the following set of parameters, which we show the full derivations in our paper. To summarize, with the material model using the three energy terms that we defined earlier, we can find parameter sets that models the four material behavior we want, namely all fluid, solid, no-slip, and free slip conditions. However, the parameters in the current frameworks need 17 parameters in 3D to describe a material. But if we look at the parameter table, we can see that the range of values that they take are very limited. This inspires us to reparameterize the material model with fewer degrees of freedom. If we take a closer look at the parameter table, we see that besides the slip boundary material, the parameters for other materials are isotropic, and within the slip boundary material, the variations in the material comes from the direction of the material. And within the isotropic materials, the variations in the material mainly comes from the weight of the frictional energy term. We therefore reparameterize the material model with these three axes of properties. We use the anisotropic value to characterize if the material is isotropic or anisotropic. And if it is anisotropic, meaning it represents the slip boundary, we use the anisotropic orientation parameter to represent the direction of the boundary. If it is isotropic, we use the fluidic parameter to represent the permeability of the fluid, with the two extremes modeling fluid and impermeable solid respectively. With this representation, we only need to specify 4 parameters to describe a material in 3D. We use nonlinear continuous interpolation functions that map these 3 properties to the parameters of the material model. The 3 material parameters can be nicely visualized as an ellipse, where the radius of the ellipse visualizes the fluidity, the eccentricity of the ellipse visualizes the isotropy, and the orientation of the ellipse visualizes the orientation of the anisotropic boundary. Because the material model and the parameterization are both continuous, we can actually continuously represent a spectrum of materials with various combinations of fluidity and anisotropy. This means our framework is fluid differentiable for materials to freely transition between fluid, solid, or boundary materials. During optimization, we can therefore initialize the design domain with a uniform intermediate material and let topology freely evolve to obtain the best geometry. To summarize, we have showed a mixture material formulation that unifies the representation of solid phase, fluid phase, and both slip and no-slip condition in a Stokes flow context. Next, I'll talk about the discretization scheme for the continuous modeling I just discussed. We discretize our domain with a Eulerian grid. We store the velocity field at grid nodes, meaning for a cell resolution of n, we obtain a nodal velocity field with resolution of n+1. We discretize the material at cell level, where within each cell the material is constant, subject to optimization. Finally, we sample subcell values with Gaussian quadrature rules. Here, I'll quickly outline the discretization for the continuous energy. For the continuous anisotropic material model we introduced, we note that all energies can be discretized into a quadratic energy form. This means essentially we're solving for a quadratic energy minimization problem subject to boundary conditions specified as Dirichlet conditions. We solve this minimization problem by constructing a KKT system. Gradient computation is straightforward with sensitivity analysis. Finally, I'll talk about our optimization framework. Our pipeline for optimization works as follows. The system takes the input of a fluidic device design task specified on the regular grid, including the locations and desired profiles of the Stokes flow, typically specified at the inlet and outlet. The system represents the fluidic device using our anisotropic mixture model in each voxel. The materials are initialized as a uniform field, and topologies evolve during optimization. A numerical differentiable simulator receives the design and solves the velocity field. The pipeline then compares the simulated flow at the outlet with the target profile and computes a loss function characterizing the difference. The loss is then backpropagated to compute gradients with respect to the anisotropic material parameters. We use MMA, which is a gradient-based optimizer, to update the design. After iterative cycles of optimization, the pipeline outputs a final design after post-processing the results. For optimization, we minimize our objective as a sum of the functional objective plus a regularizer term. The regularizer computes the compliance energy, typical in topology optimization framework, to introduce sensitivities to the system. We in addition regularize the smoothness of the anisotropy and direction. The optimization problem is subject to 2 sets of constraints. The first is a volume fraction constraint. The second are parameter bound constraints. We optimize 3 parameter fields for each cell in the design domain and initialize them as a uniform field. We use MMA as our gradient-based optimizer. Now, I'll introduce the application and optimized designs obtained from our framework. In the first application, the goal is to design a fluidic diffuser that transfers fluid from one inlet into 16 outlets, bypassing a small obstacle. The resolution of the design is 80 cubed, meaning there are in total 2 million design degrees of freedom. The specified volume fraction is 25%. On the left, we show the optimized final design. On the right, we visualize the final design slice by slice. The optimized design shows a two-level tree structure that is hollow in the middle to bypass the obstacle. This design has intricate topology that would be difficult to be specified as a prior using a shape-based representation. In the second application, the goal is to design a fluid circuit that connects inlets with varying velocities to produce equal flows at the outlets. On the high level, we want to model a water transport problem, where water sources with different pressures need to be equalized and transported to different target locations, hence the name fluid circuit. The resolution of the design is 80 cubed, with in total 2 million design degrees of freedom. We additionally run the optimization with two different volume fractions. Here, we visualize the optimization intermediate iteration using the streamlines of the velocity fields. Because our framework has a continuous representation of the solid and fluid phase, we see topology freely evolve during optimization. Here, we visualize the final design slice by slice. We ran the simulation with two different volume fraction limits, and the optimal design has different pipe connectivity. This is only possible because of the continuous formulation of our material model. Finally, we present a device that can twist a constant straight flow from a circular shaped input into twisting flow. We run the optimization under a resolution of 100 cube, meaning there are 4 million design parameters in the framework. We set the volume fraction to be 30%. Here, we visualize the optimization intermediate iteration using the streamlines of the velocity field. The inset shows the velocity field used from the outlet. We see that after optimization, the device successfully generates a twisting flow. Here, we visualize the final design slice by slice. We can see that the twisting flow is generated from a propeller-like design with rotation symmetry automatically evolved at the outlet of the system, which is very interesting given that we didn't specify any symmetry constraint in the design domain. To conclude, in this work, we propose a continuous material model that unifies the representation of solid phase, fluid phase, and both no-slip and no-slip condition. This representation allows topology to freely evolve during optimization. Our material model is capable of representing sharp interface with local surface direction, which allows us to model both slip and no-slip boundary condition. There are many possible directions to extend our work. The first is extension to Navier-Stokes flow with time variation. The second is improve the scalability of the framework with better solvers such as iterative or multi-resolution solvers. The third is to have built-in manufacturability constraint in the optimization. With that, I'll end my presentation. Thank you for listening, and if you have any questions, feel free to contact me through email.